right-hand side is applied force, left-hand side is your reacting force. K times U, stiffness times displacement, is reaction. But in dynamics, you have another force, which we already talked about, which is inertia force, mass times acceleration. So the moment mass starts accelerating, it reacts to it. So there's not only stiffness of the building trying to restore building back to its original location, but there is inertia force also helping. So this is the equation of motion. I have closed form solutions. As complicated as it looks, but it's very easy. You now have displacement of the building under this blast loading varying as a function of time. This is forced vibration zone, this is free vibration zone. I have two expressions. So all you have to do is plug in values. Omega is the frequency of the column or a wall. Then you get dynamic response of the single degree of freedom system. Okay? Now dynamic response divided by static displacement, or dynamic displacement divided by static displacement, is referred to as dynamic load factor. And dynamic load factor is one factor that is very convenient. All I have to do is know dynamic load factor. I can then do static analysis multiplied by dynamic load factor, get displacement under dynamic conditions. So it's a convenient design tool, especially if I plot maximum dynamic load factor. As I said, the ratio of duration to building period matters. If it is high, in this case 2, you can see the ratio between dynamic to static is approaching 2. I said impact load, it is 2. And if the ratio is 0.2, 1/5, then it can be lower. So once again, period of excitation and period of the structural element correlate very well. So these are the design tools, right? So if I know the ratio of duration to building period, I enter here, and my load is triangular load. Why? Because I'm looking at reflective pressure that I already quantified. Then here I get dynamic load factor. It could be 0.8. I find static displacement multiplied by 0.8. It becomes dynamic displacement. It's as easy as that. So dynamic analysis for blast purposes is fairly straightforward. There's another maximum dynamic load factor chart. This time it's a triangular load that is similar to sidewall loading. So these design aids are available. But then all of these deal with a single mass spring model, right? And you have to have concentrated lump mass for those equations and those charts to work. And you have to have concentrated load as dynamic force for them to work. But what we have is distributed mass. If I have a beam, it's distributed mass, it's not a lump mass. And if I have blast pressure, it's distributed load, not single load. So how do I go from this real element to single degree of freedom model? I have transformation factors. All I have to do is find mass of the real building or real structural element, multiply it by transformation factor for mass. I now convert it to this model. So these transformation factors are obtained from energy principles. In structural engineering, what we do, we immediately apply equilibrium principles. If we can't solve the problem, we apply compatibility principles. If we can't solve the problem, life is getting more difficult, we apply energy principles, right? So here we apply energy principles to derive transformation factors. So kinetic energy of the actual element, if you set it equal to kinetic energy of the lumped mass model, then you can find transformation factor for mass. If you equate potential energy of the real element to potential energy of the simple mass model, then you find transformation factor for resistance or stiffness. And then work done by load, distributed load versus concentrated load, you find transformation factor for load. But it so happens that transformation factor for load and for resistance are the same. Why? Because they are both related to deflected shape of the structure. If you have a triangular distribution of load or uniform distributed load, it generates different deflected shape. And stiffness is related to deflected shape, hence they are the same. So if I divide all terms with transformation factor for load, these two cancel, and I have now load mass factor. So we simplify the problem even further. All I need to know is load mass factor. I apply it to mass only, and I don't need to apply it to stiffness and load. And from that, omega is the frequency of my column or wall, and omega is equal to stiffness over mass. If I change mass to distributed mass by multiplying it by load mass factor, then I have omega for real element, but I can now get omega for the model, for which I have design tools. So that's the procedure. Very quick example, numerical example. This is a column which is a 400 millimeter square reinforced concrete column of 6 meter height. It's an industrial building made out of 40 MPa concrete. I need to know rigidity, so strength has to be specified. And it's subjected to 200 kilogram car bomb placed at 30 meters. So I immediately put in my software 200 kilograms and 30 meters and find incident pressure, reflected pressure, duration. Or I could go to UFC charts, US Department of Defense charts, those wiggly curves, and get these quantities. So first step is to convert mass of explosive and standoff distance to equivalent pressure and duration. Once I know that, then the rest is easy. And in this problem, I'm assuming that column is resisting 12 square meter of wall panel, so the pressure is acting on that area. And then I'm assuming 50% reduction due to cracking of concrete. So this is the mass per unit length. Moment of inertia, EI, gives me flexural rigidity, 50% reduction due to cracking. So I have crack rigidity. Stiffness is a stiffness coefficient. It's in every structure analysis book. So I know stiffness, I know mass, I know load mass factor to convert distributed mass to lump mass. Now I can find omega, and omega is frequency. So with that, I can then find period of the column, which is 2 pi over omega. It comes out to be 81 milliseconds. So period of the column is 81 milliseconds, and duration is given, it's 12.3 milliseconds. The ratio is 0.15, and I can enter into this chart with 0.15, read maximum dynamic load factor. That factor multiplied by static deflection. Static deflection in this case is 104, as you can see, simply found from force divided by stiffness. This is static force divided by stiffness. And then I multiply it by dynamic load factor. I get 43 millimeters, giving me deflection under dynamic load. You see, just like that, I did dynamic analysis. Once you have these charts, life becomes very easy. So here is what I did. If I want to find design moment at mid-height of this column, this is the pressure that I apply, and this is the distribution of inertia force that opposes to loss, so helping me. And then the column has its own restoring force characteristic, stiffness also helping me. So the resultant deflection is here, and this is the moment diagram. But I utilize idealized mass and force, so I treat it as if it's concentrated load and lump mass, and I get maximum moment. But this shows you that resistance is equal to applied force less the inertia force. So from that, I can find dynamic moment, which comes out to be 344 kilonewton-meters, for which I provide reinforcement and design this column if I want it to remain elastic. Okay? So here the key is remaining elastic, because when we go to building standards and codes, things may not remain elastic depending on the level of protection and performance levels that I choose as a designer. Okay? So now we're going to discuss performance-based design for blast, and that brings us to our second presentation. But maybe I should take a few minutes before you forget. If you have any questions, otherwise there will be question and answer period at the end. But if you have any burning question in your mind, you can ask now. Are there any questions on what I've covered so far? So, yes.
The equation of motion did not include the damping.
Very good question. I forgot to mention that. Of course, in the equation of motion, you have damping coefficient times velocity, which is the damping effect. Now, damping in structures is very important. If you don't have damping, things will vibrate forever. In earthquake engineering, it's very important. We consider 5% of critical damping. In blast engineering, damping is usually ignored unless you have a computer program that includes that. So, for the simple approach that I have taken, I ignore damping. Why? We're talking about 5 milliseconds. There's not enough time to go through damping, right? But during the free vibration mode, once the load is gone, obviously you can include damping to show how it will slow down and stop eventually. So damping is an option, but for simple single degree of freedom to get maximum force, it's not necessary. It's usually ignored in blast. Any other question? Okay, so let's continue, unless